Right now, light from distant galaxies is racing toward Earth, but most of it will never arrive. The universe is expanding so fast that thousands of galaxies are slipping beyond our reach every single second. Space looks empty because it's being emptied. Dark energy, an invisible force we barely understand, is tearing the cosmos apart faster than the speed of light, and there's nothing we can do to stop it. If you're enjoying this journey into the void, hit that subscribe button. We're about to witness the universe erasing itself. Prepare yourselves. We begin. Look up at the night sky. Those stars scattered across the darkness, they're an illusion of abundance. Between every point of light lies an emptiness so vast that if you shrunk our entire galaxy down to the size of a coin, the nearest galaxy would be sitting 10 feet away. And between them, nothing. Absolutely nothing. We call it space, but that word feels too generous. This isn't like the gap between cities or even continents. Imagine standing in the middle of a desert where the next grain of sand is 1,000 miles away. That's how empty the universe actually is. Matter, everything we can see and touch, makes up less than 1% of what's out there. The rest is void. Scientists measure this emptiness in light years. 1 light year equals roughly 6 trillion miles. The average distance between galaxies, 2 million light years. That means if you could travel at the speed of light, faster than anything physically possible, you'd still spend 2 million years crossing pure nothingness to reach the next island of matter. But here's what makes it terrifying. Space wasn't always this empty. After the Big Bang, matter was packed together, dense and hot. Galaxies formed close enough to interact, to collide, to dance around each other. Then, something changed. The universe started spreading apart, and it never stopped. Think of space like a balloon being inflated. Galaxies are dots drawn on the surface. As the balloon expands, those dots move farther apart, not because they're traveling through space, but because space itself is growing between them. Every second, billions of cubic miles of new emptiness appear throughout the cosmos. This expansion means the universe is becoming emptier with each passing moment. Right now, as you listen to this, the nearest galaxy to us is racing away at 40,000 miles per hour. We're not moving. It's not moving. The emptiness between us is multiplying, and this emptiness isn't passive. It has weight. Scientists call it dark energy, and it makes up 68% of everything that exists. We can't see it, can't touch it, can't detect it directly. We only know it's there because galaxies are fleeing from each other faster than gravity should allow. Here's the part that should make your skin crawl. Dark energy is getting stronger. The emptiness is growing faster now than it was 1 billion years ago, faster than it was 1 million years ago. The universe isn't just expanding, it's accelerating into oblivion. What does this mean for us? We live on a rock orbiting a star in a galaxy swimming through an ocean of nothing, and that ocean is getting deeper. Every day, the islands of matter drift farther apart. Every day, the universe becomes more hostile to everything we recognize as real. But the emptiness isn't the worst part. What's truly terrifying is what's causing it to grow. In 1998, 2 teams of astronomers made a discovery that shattered physics. They were measuring distant supernova explosions, trying to figure out how fast the universe was expanding. Every scientist expected the same answer. Expansion should be slowing down. Gravity pulls everything together, right? So, the universe should be losing speed, gradually crawling towards some eventual equilibrium. The telescope said otherwise. The universe wasn't slowing down, it was speeding up. Galaxies were racing away from each other, faster now than they were billions of years ago. Imagine throwing a ball into the air and watching it accelerate upward instead of falling back down. That's how impossible this seemed. Scientists checked their calculations 3 times, 4 times, 10 times. The math didn't lie. Something was pushing galaxies apart with more force than gravity could resist. They named this force dark energy, but that's just a placeholder for we have no idea what this is. Here's how fast we're talking. The most distant galaxies we can observe are moving away from us at 98% of light speed. That's 655 million miles per hour, and they're accelerating. In another billion years, they'll be moving even faster. This breaks one of the fundamental rules we thought governed reality. Einstein's equations suggested the universe should either expand and slow down, or collapse back on itself. A universe that expands faster and faster wasn't supposed to exist. Yet here we are, living inside one. Think about what acceleration means. When you press a gas pedal, you're adding energy. The universe is pressing its own gas pedal harder every second. Where is that energy coming from? Empty space itself. Every cubic inch of void contains a tiny amount of dark energy. As space expands, more cubic inches appear. More dark energy appears with them. The expansion feeds itself. Scientists measure this acceleration using something called the Hubble constant. It tells us how fast the universe is expanding right now. The number should be fixed, one universal speed, but measurements keep giving different answers. Some methods say 67 kilometers per second per megaparsec. Others say 74. This gap is called the Hubble tension, and it's driving physicists mad. Why does this matter? Because if we can't agree on how fast the universe is expanding, we can't predict what happens next. Is the acceleration temporary? Will it plateau? Or will it keep increasing until something breaks? The majority of evidence points to the worst option. Dark energy appears to be a constant property of space itself. As long as space exists, dark energy exists. As long as dark energy exists, expansion accelerates. There's no brake pedal, no off switch. We're passengers in a vehicle that's speeding up toward an unknown destination, and the speedometer is broken. So what exactly is this dark energy tearing everything apart? Imagine a force so powerful that it overpowers gravity across the entire universe. Not just in one region, everywhere, all at once. That's dark energy. And the strangest part? We can't see it, measure it directly, or even prove what it's made of. We only know it exists because galaxies are fleeing from each other when they should be pulled together. Think of space like a fabric. Matter creates dips in this fabric. That's gravity. A star makes a small dip. A galaxy makes a bigger one. A black hole tears a deep pit. These dips pull objects together. That's why planets orbit stars and stars cluster into galaxies. Gravity is the force trying to hold the universe together. Dark energy does the opposite. It pushes the fabric apart, not by creating hills, but by stretching the entire sheet in all directions at once. The more fabric exists, the more stretching force appears. It's like the universe has an intrinsic pressure built into empty space itself. Scientists have three main theories about what dark energy actually is. The first is called the cosmological constant. Einstein originally proposed this in 1917, then called it his biggest mistake. The idea is simple. Empty space has energy. Not much, about 1 proton's worth of energy per cubic meter. But space is infinite, so that tiny amount adds up to enough force to push galaxies apart. The second theory is called quintessence. This suggests dark energy isn't constant, it changes over time. Maybe it was weaker in the past and will grow stronger in the future. Or maybe it fluctuates like a wave, pushing and pulling. If quintessence is real, the universe's fate becomes even harder to predict. The third option is the most disturbing. Our understanding of gravity is wrong. Maybe Einstein's equations work perfectly on small scales, planets, stars, even galaxies, but fail across cosmic distances. Maybe there's no mysterious force at all. Maybe space just doesn't behave the way we thought it did. Here's the problem. Dark energy makes up 68% of the universe. Dark matter, another invisible substance, accounts for 27%. Normal matter, stars, planets, people, everything we can actually see is only 5%. We live in a universe where 95% of reality is invisible and incomprehensible, and dark energy is winning the cosmic battle. In regions where galaxy clusters sit close together, gravity still dominates. These clusters will eventually merge into massive supergalaxies. But everywhere else, dark energy is tearing structure apart. The space between galaxy clusters is expanding so fast that they'll never interact again. Picture two people standing on opposite sides of a river. The river keeps getting wider. At some point, even if they scream, sound waves can't cross the distance. Even if they shine flashlights, the light gets stretched and dimmed until it disappears. That's what's happening to galaxies. They're drifting into isolation. What makes dark energy truly terrifying isn't its strength. It's that we can't turn it off. We can't slow it down. We can't even understand it. And it's rewriting the future of everything that exists. But some galaxies are already feeling its effects in disturbing ways. Right now, at this very moment, there are galaxies moving away from Earth faster than light can travel. Not because they're breaking physics, but because the space between us is expanding so rapidly that even light can't keep up. Let's make this concrete. The Andromeda Galaxy sits 2.5 million light-years away. It's the closest large galaxy to us, and actually moving toward us due to gravity. But look beyond Andromeda, past our local neighborhood, and everything is fleeing. The Virgo cluster, 53 million light-years away, recedes at 750 miles per second. The Coma cluster, 320 million light-years distant, races away at 4,300 miles per second. Go farther. The most distant galaxies we've ever observed sit 13.4 billion light-years away. We see them as they appeared shortly after the Big Bang. The light from these galaxies has been traveling toward us for nearly the entire age of the universe. And yet, the galaxies themselves are now moving away at more than twice the speed of light. How is this possible? Because they're not moving through space. Space itself is moving. Einstein's speed limit only applies to objects traveling within space, but space itself can expand as fast as it wants. There's no cosmic speed limit on the fabric of reality. Picture yourself on a treadmill that's speeding up. You can run forward, but if the belt accelerates faster than your top speed, you'll move backward anyway. Galaxies face the same problem. Light leaves them, traveling toward us at maximum speed. But the space between us expands faster, carrying those galaxies away. The light still reaches us eventually, stretched, dimmed, ancient, but the source is now impossibly distant. Scientists call this recession velocity. It measures how fast distant objects appear to move away due to cosmic expansion. For nearby galaxies, recession is slow, a few hundred miles per second. But double the distance, and recession doubles. Triple the distance, recession triples. There's no upper limit. This creates something called the cosmic horizon. Beyond a certain distance, galaxies recede faster than light travels. Their light will never reach us, not in 1 billion years, not in 1 trillion. The space between us expands faster than photons can cross it. Those galaxies exist, but we'll never see them. They're cut off from our universe, as completely as if they existed in a separate dimension. And here's the devastating part. That horizon is getting closer. Every second, galaxies that were once visible cross beyond our reach forever. Imagine watching stars wink out of existence one by one, knowing they're still out there, but forever beyond observation. That's happening right now, just too slowly for us to notice. In 100 billion years, every galaxy outside our local cluster will have receded beyond the cosmic horizon. Future astronomers will look up and see a handful of nearby galaxies surrounded by infinite darkness. They'll have no evidence that billions of other galaxies ever existed, no evidence of the Big Bang, no evidence that the universe is expanding. They'll think they live in a small, static, eternal cosmos. They'll be wrong, but they'll have no way to know it. We're lucky. We exist in an era when the universe still reveals its secrets, when distant galaxies haven't yet vanished. But that window is closing, and it's closing because we're trapped inside an invisible barrier we can never cross. Light speed is absolute, 186,000 miles per second. Nothing moves faster. Not particles, not information, not even quantum entanglement. This isn't a technical limitation we might overcome with better technology. It's woven into the structure of reality itself. Einstein figured this out in 1905. His equations showed that as objects approach light speed, strange things happen. Time slows down, mass increases, energy requirements skyrocket. To accelerate even a single atom to light speed would require infinite energy, more energy than exists in the entire universe. This speed limit doesn't just affect spaceships, it affects everything. Gravity propagates at light speed. Electromagnetic radiation travels at light speed. Even causality, cause and effect, is limited by light speed. If you could somehow move faster than light, you'd arrive before you left. Past and future would collapse into paradox. For interstellar travel, this creates a nightmare scenario. The nearest star system, Alpha Centauri, sits 4.3 light-years away. Even if we built a spacecraft that could travel at 90% of light speed, far beyond anything remotely possible with current technology, the journey would take almost 5 years. And that's just to the nearest neighbor. Most stars in our galaxy sit thousands of light-years away. Other galaxies, millions or billions of light-years distant. At light speed, you could cross the Milky Way in 100,000 years. You could reach Andromeda in 2.5 million years. The edge of the observable universe? 93 billion light-years. Even light itself can't travel fast enough to explore what's out there. But here's where it gets worse. Remember, the universe is expanding. That expansion adds speed to the distance light must travel. A galaxy 10 billion light-years away isn't sitting still. It's racing away from us at hundreds of thousands of miles per second. Light from Earth would have to catch up to it, like a runner chasing a car on the highway. For nearby galaxies, light can still make the journey. The expansion is slow enough, but past a certain distance, about 15 billion light-years, expansion outraces light. Photons leaving Earth right now will never reach those galaxies. They'll travel forever through expanding space, getting farther from their destination with each passing second. This creates a boundary called the cosmological event horizon. It marks the limit of where we can ever send signals or information. Anything beyond it is permanently cut off from us. We can't send messages there. We can't travel there. We can't affect or interact with anything past that line in any way, ever. And that line is getting closer. As the universe expands faster, the event horizon shrinks. Galaxies that used to be within reach slip beyond it. 5 billion years from now, the horizon will be closer than it is today. 10 billion years from now, closer still. Eventually, only our local cluster of galaxies will remain inside our reachable universe. Think about what this means. 99.9% of galaxies that exist right now are already beyond our reach. We can see them. Their ancient light is still arriving, but we can never visit them, never communicate with them. If intelligent life exists in those galaxies, we'll never know. They're seeing the same problem from their side, looking at us, forever separated by space that expands too fast to cross. We're not just limited by technology, we're imprisoned by the laws of physics themselves, and the walls of that prison are closing in. But even the galaxies we can still see are about to disappear from view forever. Imagine looking up at the night sky 100 billion years from now. You'd see a handful of galaxies, maybe 30 or 40, scattered across the darkness. Everything else? Gone. Not destroyed. Not dead. Just invisible, carried so far away by cosmic expansion that their light can no longer bridge the gap. This isn't speculation. Astronomers have calculated exactly when galaxies will vanish from our view. The process has already begun. Right now, we can observe roughly 200 billion galaxies across the universe. That number sounds enormous, but it's a tiny fraction of what actually exists. For every galaxy we can see, countless others sit beyond our cosmic horizon, their light eternally unable to reach us. The mathematics is straightforward, but brutal. Light travels at a fixed speed. Space expands at an accelerating rate. At some distance, expansion wins. The space between us and a galaxy grows faster than light can cross it. Photons leaving that galaxy right now will travel toward us for billions of years, making progress, getting closer, but never quite arriving because the finish line keeps moving away faster than they can run. Here's how the disappearance unfolds. First, the most distant galaxies fade from view. These are the ones sitting near the edge of our observable universe, already moving away at nearly light speed. Their light grows dimmer and redder as space stretches the wavelengths, until the photons arrive so infrequently that even the most sensitive telescopes can't detect them. These galaxies don't blink out. They fade like a sunset, gradual and inevitable. Next, galaxies closer to home start vanishing, not because they're physically moving away faster. Cosmic expansion affects everything equally, but because time keeps passing. As billions of years roll by, the cumulative effect of expansion grows. Galaxies that once sat within our reach cross beyond the point of no return. Their light stops arriving. Their existence becomes unprovable. Scientists have mapped this timeline. In 150 billion years, every galaxy beyond our local supercluster will have disappeared from view. The Virgo supercluster, home to thousands of galaxies spanning 110 million light-years, will be the last major structure we can observe before the darkness closes in. But even Virgo won't last forever. Eventually, dark energy will tear apart even large gravitational structures. Galaxy clusters will disperse. Individual galaxies within our local group will remain visible, but everything else vanishes. The night sky becomes a void, punctuated by a few dozen familiar neighbors. This creates a horrifying scenario for any civilization that might arise in the far future. Imagine being an astronomer trillions of years from now. You'd look up and see a small, seemingly eternal collection of galaxies. No evidence of the Big Bang. Its radiation would be too weak to detect. No evidence of cosmic expansion. Nothing visible to measure it against. No evidence that the universe was ever different than it appears right now. You'd develop theories about your static, unchanging cosmos. All of them would be wrong, but you'd have no way to know that. The truth of the universe, its origin, its expansion, its ultimate fate, would be completely hidden from you. Not because the evidence was destroyed, but because it receded beyond observation. We exist in a brief golden age, a cosmic moment when the universe reveals its nature, when distant galaxies still shine in our telescopes, when we can study the afterglow of creation itself. That window is closing. Future civilizations will inherit a darker, emptier sky. They'll look up and see loneliness, and they'll have no idea how much they're missing. Picture this. You're born on Earth 1 trillion years from now. You grow up looking at a night sky containing exactly 34 galaxies. That's it. No distant clusters, no quasars, no cosmic web of structure stretching across billions of light years. Just 36 island galaxies floating in an ocean of perfect blackness. You become an astronomer. You study those galaxies meticulously. You measure their positions, their movements, their compositions. Over decades of observation, you notice something strange. They're all drifting closer together. Gravity is pulling them inward. You conclude that the universe is contracting, that everything visible is falling toward everything else. You'd be wrong, but you'd have no evidence to prove it. The universe wouldn't be contracting, it would still be expanding, faster than ever. But the only galaxies you can observe are the ones bound together by gravity into our local cluster. These galaxies orbit each other, immune to cosmic expansion, because their mutual gravitational pull is stronger than dark energy's push. To you, they look like the entire universe, and they're moving together because that's what gravitationally bound objects do. You'd never observe the Big Bang's cosmic microwave background. It would still exist, but stretched and cooled by trillions of years of expansion, until its temperature sits just a fraction above absolute zero. Your instruments couldn't distinguish it from empty space. You'd have no evidence the universe had a beginning. You'd never measure cosmic expansion. All the galaxies fleeing from each other at impossible speeds? Gone, vanished beyond your cosmic horizon. The only galaxies left in view are the ones coming closer, making it seem like the universe is contracting or static. You'd never see distant supernovae, the ones that prove dark energy exists in the first place. You'd develop theories about gravity, matter, energy, all based on incomplete information. Your physics would work for what you can see, but it would miss the bigger truth entirely. This isn't science fiction. This is the actual future awaiting any civilization that arises late in cosmic history. Astronomers in that era will look at the same universe we study, but they'll see something completely different. Not because the universe changed its rules, but because observable reality depends on when and where you exist. Scientists call this cosmic censorship. The universe hides its past from future observers, not through malice, but through expansion. The evidence doesn't disappear, it just recedes beyond the speed of light barrier, becoming forever unreachable. Here's what makes this terrifying. We might be experiencing the same problem right now. Maybe there's evidence of an even larger truth that's already vanished beyond our cosmic horizon. Maybe the universe went through earlier phases that we can never observe because their light has been outrun by expansion. Maybe what we think is the complete history of the cosmos is actually just one chapter in a much longer story. We can see 13.8 billion years into the past, back to the Big Bang itself, or at least back to what we call the Big Bang. What if that wasn't the beginning? What if something happened before, but the evidence has already receded beyond detection? We'd be just like those future astronomers, studying an incomplete picture and thinking it's everything. This is the cruelest aspect of cosmic expansion. It doesn't just separate galaxies in space, it separates civilizations across time from the truth of their own universe. Every generation of astronomers sees less, knows less, can prove less. We're living in one of the last eras when the universe is still knowable, when its origin, its structure, its fate are all still visible in our telescopes. In the far future, that knowledge vanishes. Not because civilizations forget it, but because the universe itself erases the evidence. And the process has already begun. Right now, as you hear these words, we're trapped inside a shrinking bubble of knowable space. Stand outside on a clear night. Look up. Every star, every galaxy, every photon of light reaching your eyes comes from inside a sphere. That sphere is the observable universe, and it has a hard edge. Beyond that edge, galaxies exist. Stars burn, planets orbit, but their light will never reach us. Not in a billion years, not in a trillion, never. The edge sits 46.5 billion light-years away in every direction, not 13.8 billion. That's just how long light has been traveling toward us. The actual distance is greater because the universe expanded while that light was in transit. Picture a runner on an expanding track. By the time she reaches the finish line, the starting point has moved farther back than where she began. But here's where it gets strange. That edge is both real and imaginary. Real because it marks a genuine boundary. Nothing beyond it can ever affect us. Imaginary because there's nothing special about the location itself. An observer in a galaxy at the edge of our observable universe has their own sphere centered on them. Their observable universe overlaps with ours, but extends into regions we can never see. Think of it like standing on an island in fog. You can see 3 miles in every direction. That's your visible world. Someone standing 3 miles away has their own circle of visibility, overlapping yours but revealing shoreline you can't observe. Neither of you is at the center of anything special. You're both just standing in fog. except the cosmic fog is expanding, and as it expands, your visible range shrinks. This seems backwards at first. The universe is getting bigger. Shouldn't we be able to see more? But the expansion is accelerating. Light from distant galaxies has to cross an ever-growing distance. Eventually, expansion outraces the light. Galaxies slip over the edge of our sphere and vanish from view. The observable universe has been shrinking for billions of years. Not shrinking in the sense that the edge is getting closer, it's actually getting farther away in absolute distance. But shrinking in the number of galaxies we can observe. Every day, more galaxies cross the threshold where their light can no longer reach us. The population of our visible universe is dropping. Right now, we can observe approximately 200 billion galaxies. In 50 billion years, that number drops to 100 billion. In 100 billion years, it drops to 50 billion. The observable universe becomes smaller and emptier with each passing epoch. And here's the part that should make you deeply uncomfortable. We have no idea how large the actual universe is beyond what we can see. It might extend another 46 billion light years and then stop. Or it might be infinite, stretching forever in all directions with no edge whatsoever. We can't know. We're trapped inside our observation sphere with no way to peek beyond it. Some physicists estimate the entire universe is at least 250 times larger than the observable portion. Others suggest it's infinite. Both possibilities are equally strange. A universe with an edge raises the question, what's beyond it? A universe without an edge raises the question, how can something have no boundary? Either way, we're confined. The observable universe is our prison cell, and the walls are closing in. Not rapidly. The process takes billions of years, but inexorably. Every cosmic tick of the clock, more galaxies slip away, more stars vanish, more of reality becomes unreachable. You might think, so what? If those galaxies are so far away that light can't reach us anyway, they're not relevant to our existence. But they are, because hidden in those unreachable regions might be answers to questions we can't solve. The nature of dark energy, the beginning of the universe, whether our physics is complete or just an approximation that breaks down at larger scales. We're trying to solve a puzzle while pieces of it fall off the table faster than we can grab them, and we can't even see how many pieces are left. But the shrinking edge isn't the only thing trapping us. We're also confined by something far more absolute. Here's the truth about our cosmic prison. We can't leave it. Not with better rockets. Not with generation ships. Not with any technology we could ever conceivably build. The observable universe isn't just the region we can see. It's the region we can ever interact with in any way. And that region is surrounded by an impenetrable wall. That wall is causality itself. Information can't travel faster than light. Cause and effect are limited by light speed. This means any galaxy beyond our cosmic horizon might as well exist in a separate universe. We can't send signals there. We can't receive signals from there. We can't affect it, and it can't affect us. The connection is permanently severed. Let's make this concrete. The Andromeda Galaxy sits 2.5 million light-years away. If we launched a spacecraft tomorrow, traveling at half the speed of light, wildly optimistic with current technology, it would reach Andromeda in 5 million years. Difficult, but theoretically possible. Now consider a galaxy sitting 15 billion light-years away. It's receding from us at over 90% of light speed. If we launched the same spacecraft toward it, what happens? The craft would travel forward at half light speed, but space between us and that galaxy expands faster. The spacecraft makes progress, moving away from Earth, but the destination races away faster. The gap widens despite the craft's forward motion. It's like running up a down escalator that's moving faster than you can climb. You're running as hard as you can, making all the right motions, but you're going backward anyway. That spacecraft could travel for trillions of years and never get closer to its target. This creates a fundamental limit on where we can go. not a limit based on technology, but on physics itself. Roughly 94% of the observable universe is already beyond our reach. We can see it in our telescopes, ancient light still arriving, but we'll never visit it. Those galaxies are receding faster than light can chase them. The remaining 6%, the local universe within a few billion light years, is still theoretically reachable, but that region is shrinking. As cosmic expansion accelerates, more nearby galaxies cross the threshold into unreachability. In 5 billion years, the Milky Way and Andromeda will merge into a single supergalaxy. That combined structure, along with about 50 smaller galaxies in our local group, will remain gravitationally bound. Everything else vanishes beyond the wall. In 100 billion years, our local group will be the only matter we can interact with. We'll be confined to a bubble containing perhaps a few dozen galaxies spanning a few million light years. Beyond that, infinite expansion, galaxies fleeing faster than we can follow, light that will never arrive, signals that can never be sent or received. Future civilizations in our galaxy will look out and see a small cluster of neighboring galaxies. They might wonder what lies beyond. They'll point their telescopes into the darkness and find nothing. Not because nothing is there, trillions of galaxies still exist, but because causality has severed the connection. Think about what it means to be permanently cut off from 94% of reality. It's not like being on an island where you might build a boat someday. It's like being in a universe that's splitting into fragments, each fragment drifting away from the others faster than light itself. You can watch your neighboring fragments recede into darkness, knowing you'll never reach them no matter how long you try. We're living through the moment when the universe fractures, when one unified cosmos breaks into countless causally disconnected regions. The walls of our bubble are already hard. They're just still far enough away that we don't feel confined yet. But we should feel confined, because there's something out there in the darkness and we're being pulled toward it against our will. Turn on a flashlight and point it at the sky. Those photons will travel forever, across the solar system, between the stars, through the Milky Way, out into intergalactic space. They'll keep moving at light speed for billions of years, and they'll never arrive anywhere. This is the reality of cosmic expansion. Light leaving Earth right now is headed toward distant galaxies, but most of those galaxies are receding so fast that the light will never catch up. Imagine a photon leaving our planet today, traveling toward a galaxy 15 billion light years away. That photon moves at light speed, but the space between here and there expands faster than light can cross it. The photon makes progress, gets farther from Earth, crosses millions of light years, and yet the destination keeps receding faster, staying forever out of reach. Now flip it around. Galaxies beyond a certain distance are shining light toward us right now. That light is traveling at maximum speed, headed directly for Earth, but it will never arrive. The space between us expands too quickly. Those photons are trapped in an expanding void, making progress but never closing the gap. They'll travel through space for the entire remaining lifetime of the universe without ever reaching us. This creates something deeply strange. There are galaxies that exist, that are real, that are currently shining brightly, but we will never see them, not in any telescope, no matter how powerful, not in any wavelength of light, not through any trick of physics. They're permanently invisible to us, not because they're too dim or too far, but because the light they emit can never bridge the expanding space between us. Think about what this means for first contact. If intelligent life exists in those galaxies, we'll never know. They could be broadcasting radio signals, building megastructures, lighting up their entire galaxy with fusion torches. None of it matters. Their signals travel at light speed, and light speed isn't fast enough. The messages exist, propagating through space, but they'll never deliver. Worse, they're probably trying to reach us. Any civilization advanced enough to broadcast signals would eventually point their telescopes at galaxies like ours. They'd see our type of star, our type of galaxy, and think, maybe someone is there. so they'd send a message, beamed directly at us with perfect accuracy. And that message would travel through expanding space for trillions of years without ever arriving. We'd never hear it, never know it was sent, never have any evidence those beings existed. The same applies in reverse. If we sent signals toward the most distant galaxies right now, those transmissions would be doomed before they left Earth. We'd be shouting into an expanding void, our voices eternally unheard. But here's where it gets truly disturbing. Scientists estimate there are 2 trillion galaxies in the observable universe. That's all the galaxies we can theoretically see if we had perfect telescopes. But that number only includes galaxies whose light has already reached us or will reach us someday. There are countless other galaxies beyond the cosmic horizon. Galaxies that exist, that have always existed, but whose light will never reach Earth under any circumstances. How many? We can't know. Maybe 10 trillion, maybe 100 trillion, maybe an infinite number. They're out there right now, forming stars, possibly harboring life, existing in the same space and time as us. But they're cut off from our universe as completely as if they inhabited a separate dimension. The universe is partitioned into causally disconnected regions. Each region contains galaxies that can interact with each other, but not with galaxies in other regions. We live in one such region, a bubble of galaxies whose light can still mix and mingle. Beyond our bubble, other bubbles, other collections of galaxies, equally real, equally important, but forever beyond our reach. This means when we talk about the universe, we're really only talking about our local region of it, our cosmic bubble. The real universe, the full universe, is vastly larger and almost entirely unknown to us. We're like a fish in a pond trying to understand the ocean. We can study our pond in detail, but the ocean stretches beyond in ways we can't even begin to measure. And our pond is being ruled by an invisible tyrant pulling everything toward an unknown destination. The Milky Way is moving, not just expanding with the universe, actively traveling through space at 370 miles per second. That's roughly 1 million miles per hour. And it's not moving randomly, it's being pulled toward something. Scientists discovered this motion in the 1970s. They were mapping the cosmic microwave background, the afterglow of the Big Bang, expecting it to look perfectly uniform. Instead, they found a dipole pattern. One side of the sky appeared slightly warmer, the other slightly cooler. This wasn't random. It meant we were moving through space fast enough to create a Doppler shift in the ancient radiation. The obvious question, moving toward what? Astronomers traced the direction of our motion and found something alarming. There's a region of space about 150 million light-years away, where tens of thousands of galaxies are converging, all of them pulled by tremendous gravitational force toward a single location. Scientists named it the Great Attractor. Here's the disturbing part. We can't see it. The Great Attractor sits behind the zone of avoidance, a thick band of dust and gas from our own galaxy that blocks visible light from distant objects. Infrared and radio telescopes can peer through the dust, revealing massive galaxy clusters in that direction. But the total mass visible doesn't explain the gravitational pull we're experiencing. Something is out there. Something with roughly 10 quadrillion times the mass of our galaxy. We're being pulled toward it like water circling a drain, and we have no idea what it actually is. Some scientists think the Great Attractor is just a concentration of dark matter, an invisible clump of gravitational mass that doesn't shine but pulls everything nearby toward it. Others suggest it might be a supervoid, a region where space expanded differently, creating a gravitational wake that pulls matter inward. The most disturbing theory? The Great Attractor might be a precursor to a future collision event. Tens of thousands of galaxies converging on a single point, eventually creating a supercluster of incomprehensible scale. But wait, it gets stranger. In the 1990s, astronomers discovered we're not just being pulled toward the Great Attractor, we're being pulled past it. There's something even larger, even farther away, exerting influence across even more mind-boggling distances. They call this the Shapley concentration, a supercluster containing more than 8,000 galaxies. It sits 550 million light-years away and contains about 10,000 times the mass of our galaxy. Think about the scales involved. We're one galaxy among 200 billion in the observable universe. We're part of a local group containing about 50 galaxies. That group belongs to the Virgo supercluster, which contains about 100,000 galaxies, and our entire supercluster is being pulled toward the Shapley concentration like debris in a current. This reveals something terrifying about cosmic structure. Matter isn't distributed evenly. There are regions of incredible density, superclusters containing thousands of galaxies, separated by vast voids where almost nothing exists, and these density differences create gravitational flows. Matter streams from low-density regions toward high-density regions like water flowing downhill. We're caught in one of those flows. The Milky Way, Andromeda, and all our neighboring galaxies are falling toward a supermassive concentration of matter hundreds of millions of light-years away. We're moving at over 1 million miles per hour, and we've been falling for billions of years. We might continue falling for billions more before we reach the destination. What happens when we arrive? Nobody knows. Maybe we'll settle into orbit around the Shapley concentration, becoming part of its gravitational structure. Maybe we'll pass through and continue onward, pulled by even larger structures we haven't discovered yet. Or maybe, just maybe, cosmic expansion will eventually overpower the gravitational attraction, leaving us forever falling toward a destination we can never reach. The most unsettling aspect of the Great Attractor isn't the pull itself. It's the realization that galaxies aren't randomly scattered through space. They're caught in invisible currents, flowing along predetermined paths carved by gravity and dark matter. We like to think of ourselves as isolated, autonomous, free to chart our own course through the cosmos. But we're not. We're being pulled toward unknown destinations by forces vastly larger than ourselves. And between the currents, in the spaces where nothing flows, there exist regions so empty they break our understanding of reality itself. Imagine a sphere of space 1 billion light-years across. Inside that sphere, count the galaxies. In a typical region of the universe, you'd find roughly 10,000 galaxies. Stars, planets, gas, dust, dark matter, all the usual cosmic ingredients. Now imagine the same sphere somewhere else. You count the galaxies again. This time you find 10, not 10,000. 10 total galaxies scattered across 1 billion light-years of emptiness. The rest is just void. No stars, no planets, no gas. Nothing but space, expanding into more space. These regions exist. Astronomers call them cosmic voids, and they're the largest structures in the known universe. They're not empty in the sense of perfect vacuum. A few galaxies do exist within them, usually small and dim. But compared to the rich galaxy clusters that surround them, voids are essentially barren. 95% of space sits inside these empty regions. The typical void spans roughly 150 million light-years across, but some are much larger. The biggest known void, called the Eridanus supervoid, stretches 1 billion light-years in diameter. If you stood at its center and looked in any direction, you'd see almost nothing. The nearest galaxy cluster would be hundreds of millions of light-years away. You'd be surrounded by darkness so complete that you could travel at light speed for 30 million years before reaching the edge. Here's what makes voids so disturbing. They shouldn't exist according to our best models of cosmic structure. After the Big Bang, matter should have spread out relatively evenly. Gravity would cause slight clumping, regions where matter bunched together into stars and galaxies. But the clumping should be mild, small-scale clustering with smooth transitions between dense and sparse regions. That's not what we see. We see a cosmic web, long filaments of galaxy clusters stretching across hundreds of millions of light-years, surrounding vast bubbles of emptiness. The universe looks like foam or Swiss cheese, dense walls of matter enclosing hollow voids. This structure is too organized, too extreme. The density differences between the filaments and the voids are larger than early universe models predicted. Scientists have three theories about how voids formed. The first suggests they're regions where dark matter and normal matter happen to be slightly less dense shortly after the Big Bang. As gravity pulled matter together elsewhere, these underdense regions became even emptier. Matter flowed out of them like water draining from high ground, leaving behind deserts of space. The second theory proposes that voids are repeller zones. Dark energy doesn't just expand space uniformly, it pushes matter away from certain regions and toward others. Voids mark the places where dark energy's repulsive force is strongest, actively ejecting matter toward the denser filaments. The third theory is the most unsettling. Maybe voids aren't places where matter never formed. Maybe they're places where matter used to exist, but was consumed. Imagine primordial black holes. Black holes formed shortly after the Big Bang, gathering in certain regions and devouring everything around them. Eventually, these black holes would evaporate through Hawking radiation, leaving behind empty space with no trace of what happened. No matter which theory is correct, voids are growing. As the universe expands, the empty regions get emptier. The few galaxies currently inside voids are slowly drifting toward the walls. In billions of years, even those stragglers will join the filaments, leaving the voids completely barren. This creates a disturbing vision of the universe's future. All matter will eventually cluster into narrow filaments and walls, separated by expanding voids that contain nothing at all. The universe will resemble a vast empty arena with thin threads of matter stretched across it. The voids will dominate, making up 99% of space. The matter will be confined to 1%. And here's the part that should chill you. We live in a relatively dense region. The Milky Way sits inside the Virgo supercluster, surrounded by thousands of other galaxies. We look up and see a sky full of stars because we inhabit a cosmic city. But most of space isn't like this. Most of space is void. If Earth had formed inside one of these empty regions, our ancestors would have looked up and seen almost nothing, a handful of dim galaxies, vast darkness. They would have assumed the universe was small and lonely because their location made it seem that way. We're lucky to live where matter exists, but that luck is temporary. As cosmic expansion continues, even our local cluster will become increasingly isolated. The voids will grow, the filaments will thin, the darkness will close in. And in certain directions, the darkness already hides something inexplicable. In 1977, astronomer Robert Kirshner was mapping galaxies in the constellation Boötes. He expected to find the usual distribution, clusters of galaxies scattered across the sky, roughly evenly spaced. Instead, he found a hole, not a small gap, not a minor underdensity, a spherical region 330 million light-years across, containing almost no galaxies whatsoever. Where there should have been approximately 10,000 galaxies, he found 60 scattered specks of light in a void so large you could fit the Milky Way inside it 2,000 times. The Boötes void, later nicknamed the Great Nothing, remains one of the most perplexing structures in astronomy. It's not the largest void we've discovered, but it might be the emptiest. The galaxy density inside is 10% of what it should be. 90% of the matter that should exist there is simply missing. Let's put the scale in perspective. Light takes 330 million years to cross the Boötes void. If you started traveling through it at light speed when the first dinosaurs appeared on Earth, you'd be about 3/4 of the way across right now. The void is so large that dozens of galaxy superclusters could fit inside with room to spare. And yet, it's almost perfectly empty. The few galaxies that do exist there are small, dim, and widely separated. Most of them cluster near the edges, as if they're trying to escape. The interior is just darkness and expanding space. The disturbing question: where did the matter go? When astronomers model galaxy formation, they input the density fluctuations measured in the cosmic microwave background, the oldest light in the universe. These fluctuations tell us how matter was distributed shortly after the Big Bang. The models predict voids should exist, but nothing as extreme as Boetes. There should be at least 5 times more galaxies inside than we actually observe. 3 possibilities exist. First, the matter is still there, but it's dark. The missing galaxies never formed stars. All their matter collapsed into dark structures, black holes, failed galaxies, massive clouds of cold gas. This seems unlikely. Star formation is efficient, even in the emptiest regions of space. At least some stars should ignite. Second, the matter left. Gravity from surrounding structures pulled galaxies out of the void toward denser regions. Over billions of years, the void emptied itself as matter flowed toward the walls. But this doesn't fully explain the extreme underdensity. Even with efficient drainage, more galaxies should remain. Third, the matter was never there in the first place. The Boetes void marks a region where the Big Bang's initial distribution of matter was unusually uniform. No clumps, no density variations, just smooth, featureless space, with no gravitational seeds, no galaxies formed. This theory matches observations better, but it raises new questions. Why would one region be so different from everywhere else? What made that patch of early universe special? Some cosmologists suggest voids like Boetes are evidence that our models of the Big Bang are incomplete. Maybe the universe didn't start with tiny random fluctuations that grew into galaxies. Maybe there were larger structures present from the beginning, vast regions of high and low density carved into space before stars ever formed. Others wonder if voids are scars from an earlier era. If the universe went through a previous phase before the Big Bang, a collapse or bounce or transition, voids might mark places where energy drained away during that event. They'd be cosmic wounds that never healed. The most unsettling possibility: voids are growing. Not just expanding with space, but actively consuming matter. Dark energy's repulsive force might be stronger inside voids, pushing galaxies outward faster than they can be pulled back by gravity. If this is true, then voids aren't just empty. They're getting emptier, and they're spreading. We can test this. Measure galaxies near void edges. Track their motions over time. If they're being pushed away from the void center, we'll know the emptiness is active, aggressive, infectious. If they're falling toward the walls, voids are passive, just regions that started empty and stayed that way. Either way, the Boetes void forces us to confront an uncomfortable truth. The universe isn't just expanding, it's fragmenting. Dense regions cluster together while empty regions remain empty. Matter concentrates into smaller and smaller volumes of space, while the voids grow larger. The cosmos is sorting itself, separating matter from emptiness, light from darkness, and the process might be accelerating faster than we ever imagined. The voids aren't static. They're not fossil remnants of the early universe that have remained unchanged for billions of years. They're alive, growing, consuming the space around them like cancerous bubbles expanding through tissue. Here's how it works. Picture a void with galaxy clusters around its edges. Gravity pulls those galaxies together, making the clusters denser. But gravity has a limited range. Beyond a certain distance, its pull becomes weak. Dark energy, meanwhile, operates everywhere. Inside the void, there's almost no matter to counteract dark energy's repulsive force. The space expands faster there than in denser regions. Over time, this creates a feedback loop. The void expands. Its expansion pushes nearby galaxies outward. Those galaxies drift toward existing clusters at the void's edge, making the clusters denser while leaving the void even emptier. The emptier the void becomes, the faster it expands. The faster it expands, the more it pushes galaxies away. the cycle accelerates. Scientists measure this by tracking peculiar velocities, the motion of galaxies relative to the cosmic expansion. If galaxies were just floating along with expansion, they'd all move away from each other at predictable speeds, but they don't. Galaxies near voids move faster than expected, accelerating away from the empty regions. Galaxies near massive clusters move slower, or even toward the clusters, pulled by gravity. This creates a flow pattern. Matter streams out of voids and into filaments. The filaments feed into galaxy clusters. The clusters grow denser, while the voids grow emptier. The universe is segregating itself, concentrating matter into smaller volumes while expanding the empty spaces between them. Current measurements show voids are expanding about 10% faster than the average cosmic expansion rate. That might not sound like much, but compounded over billions of years, it's enormous. A void that's 100 million light-years across today will be 200 million light-years across in 10 billion years, and 300 million light-years across in 20 billion years. The growth is exponential. This has terrifying implications for the universe's long-term structure. Right now, matter is organized into a cosmic web, filaments and clusters, separated by voids. But as voids expand, the filaments will thin. Galaxy clusters at the nodes of the web will merge into superclusters. Eventually, each supercluster will become an isolated island of matter surrounded by an exponentially growing void. The Laniakea supercluster, our cosmic neighborhood containing 100,000 galaxies, will eventually stand alone. Every other supercluster will recede beyond our cosmic horizon, carried away by the expanding voids between us. We'll be left with our local matter, surrounded by emptiness, stretching in every direction. And it gets worse. Dark energy's strength appears constant, meaning voids will never stop growing. There's no equilibrium state where expansion and gravity balance out. The voids will expand forever, growing faster as they become emptier. The spaces between matter will become so large that even light will struggle to cross them. Think about what this means for cosmic communication. Right now, different galaxy clusters can still exchange information. Light from one cluster can reach another in hundreds of millions of years. But as voids grow, the distances increase. Eventually, light leaving one cluster will never reach another, not because the destination is receding too fast, but because the void between them is expanding faster than light can cross it. Each supercluster will become causally isolated, cut off from every other concentration of matter in the universe. There'll be island universes, small pockets of structure floating in an infinite ocean of expanding emptiness. Any civilizations in those islands will look out and see nothing but darkness. They'll have no evidence other superclusters exist, no way to communicate with them even if they knew they were there. We're witnessing the early stages of this fragmentation right now. The voids we observe today are the seeds of future isolation. The emptiness growing between galaxy clusters is the beginning of a process that will ultimately separate the universe into countless unreachable regions. Some scientists estimate we have about 150 billion years before the voids expand enough to isolate our local supercluster completely. Others think it could happen sooner, perhaps as soon as 50 billion years, depending on how dark energy's strength evolves. Either way, the clock is ticking, the voids are growing, the universe is coming apart, and there's nothing we can do to stop it. But the voids aren't the only mystery eating away at the fabric of space. In 2004, astronomers analyzing the cosmic microwave background discovered something wrong. Most of the sky showed the expected pattern, tiny temperature fluctuations around 2.7 degrees above absolute zero. But one region, about 10 degrees across, in the constellation Eridanus, was different, colder, about 70 microkelvin colder than the surrounding regions. That might sound tiny, 70 millionths of a degree, but at cosmic scales, it's enormous. The cosmic microwave background is the most uniform thing in nature. temperature variations are typically 100,000 times smaller than what we see in the cold spot. This wasn't a small anomaly. This was a statistical impossibility showing up in our telescopes. Scientists call it the CMB cold spot, and 13 years after its discovery, we still don't understand it. The simplest explanation is that it's just a random fluctuation. Probability says that even incredibly unlikely events should happen somewhere in a large enough dataset. The problem? We've calculated the odds. The chance of a cold spot this large appearing randomly in the cosmic microwave background is roughly 1 in 50,000. Possible, but suspicious. Other explanations are stranger. One theory suggests the cold spot is caused by a supervoid, a region of space larger than we've ever observed, extending billions of light years across. As light from the cosmic microwave background travels through this void, it loses energy climbing out of the void's gravitational well. This makes the light appear colder in that direction. The numbers almost work. We do find an unusually large void in the direction of the cold spot, about 1.8 billion light-years across. But when physicists calculate how much cooling that void should cause, they get a number far smaller than what we observe. The void helps explain the cold spot, but it's not the complete answer. A more disturbing theory: the cold spot is evidence of a collision, not between galaxies or even between galaxy clusters, but between universes. If our universe is one bubble in an infinite multiverse, and if another bubble once collided with ours, the impact would leave a scar, a region where the fabric of space was compressed or depleted. The cosmic microwave background in that region would appear colder because energy was lost during the collision. This sounds like science fiction, but the mathematics is sound. Multiverse theories that arise from cosmic inflation predict exactly this kind of signature. A cold, underdense region roughly 10 billion light-years across, appearing as a circular spot in the cosmic microwave background. The cold spot matches this prediction almost perfectly. The implications are staggering. If the cold spot is a collision scar, it means other universes exist, not as abstract mathematical possibilities, but as physical regions of space that once touched our own. It means our universe has boundaries, edges where it interfaces with other bubbles. It means reality is vastly larger and stranger than we ever imagined. But we can't prove it. The cold spot sits at the edge of our observational limits. We see the temperature anomaly. We see the void beneath it. We can measure and remeasure and analyze the data. But we can't run experiments. We can't visit the region and inspect it up close. We're limited to interpreting photons that have been traveling toward us for 13.8 billion years. Some scientists remain skeptical. They point out that the cold spot could be caused by foreground contamination, dust or gas in our own galaxy, blocking or scattering the background radiation. Or it could be an instrumental artifact, some subtle, systematic error in how the satellite measured that patch of sky. These explanations are boring but plausible. The frustrating part is that we might never know for certain. The cold spot exists at the boundary between what we can observe and what we can explain. It's either a random fluke, a supervoid, or evidence of a cosmic collision. Each explanation is possible. None is proven. What makes the cold spot truly unsettling isn't just its existence, it's what it represents. A reminder that the universe can show us anomalies we're not equipped to understand, patterns that break our models, mysteries that sit right in front of us, visible in our best telescopes, and yet remain unsolved. And the cold spot isn't even the strangest thing moving through space. In 2008, a team of astronomers noticed something impossible. They were tracking the motion of galaxy clusters using X-ray observations, expecting to see random movements in all directions. Instead, they found a pattern. Hundreds of galaxy clusters were moving in the same direction, all of them flowing like a river through space. They called it dark flow, and it shouldn't exist. According to cosmology, galaxy clusters should move randomly, pulled by nearby gravitational sources, but with no overall preferred direction. The universe should look the same in every direction, with no large-scale flows or currents. That's a fundamental principle called isotropy. Dark flow breaks that principle. The clusters are moving toward a specific point in the sky, in the constellation Centaurus, at speeds up to 600 miles per second. That's over 2 million miles per hour, and they're moving coherently, all in the same direction, as if pulled by a single massive source. The problem: there's nothing in that direction, no supercluster, no unusual concentration of matter, nothing visible that could cause such powerful attraction. Scientists have scanned the region with every telescope available: optical, infrared, radio, X-ray. They find galaxy clusters, sure, but nothing special. Nothing that should pull hundreds of other clusters toward it. So what's causing the flow? One possibility is that dark matter is distributed unevenly at scales larger than we've measured. Maybe there's a massive concentration of invisible matter sitting just beyond our observable universe's edge. Its gravity reaches into our cosmic bubble, pulling galaxy clusters toward it. We can't see the source because it lies beyond where light can reach us, but we can see its gravitational influence. Another theory suggests dark flow is leftover momentum from the universe's earliest moments. During cosmic inflation, the brief period when space expanded exponentially right after the Big Bang, some regions might have inherited a preferred direction of motion. That motion persists today, carrying galaxy clusters along predetermined paths carved by ancient physics. The most unsettling explanation: dark flow is evidence of structure beyond our universe. If the Big Bang created multiple cosmic bubbles, separate regions of space with their own physics, then massive structures in neighboring bubbles could exert gravitational pull across the boundaries. We'd see clusters in our universe flowing towards something we can never observe, pulled by matter that exists outside our reality. This last possibility is deeply troubling. It suggests our observable universe isn't the whole story, that there are external forces acting on us from regions we can't see, can't measure, and can't ever visit. We're not isolated. We're not independent. We're being influenced by something beyond our cosmic horizon. But here's where the controversy begins. Not all scientists agree dark flow exists. Some measurements confirm it, others don't see it at all. The effect is subtle. Measuring galaxy cluster velocities is difficult, and small systematic errors can create false signals. Teams using different methods get different results. Some see coherent flow, others see random motion. The debate has raged for over 15 years. Papers are published claiming dark flow is real. Counterpapers appear claiming it's an artifact. The astronomy community remains split. Without consensus, dark flow exists in a strange limbo, observed by some, denied by others, impossible to verify conclusively. What makes this frustrating is that dark flow, if real, would be profoundly important. It would prove the observable universe isn't everything. That structure exists at scales larger than we can directly measure, that our cosmic bubble is embedded in something vastly larger. These are fundamental questions about the nature of reality itself, yet we can't answer them. The evidence is right at the threshold of what our instruments can detect. Slightly better measurements might confirm dark flow, or they might reveal it was always a mistake. We're stuck in the worst possible position, tantalizing hints of something revolutionary, but no way to prove or disprove them. And even if dark flow is real, it pales in comparison to the fundamental problem we face. The universe might be infinite, and we'll only ever see the tiniest fraction of it. Stand outside tonight and look up. Count every star you can see, maybe a few thousand on a clear night. Those stars are all inside the Milky Way, our home galaxy containing 200 billion stars total. Now think bigger. Our galaxy is one of 200 billion galaxies in the observable universe. That's about 40 billion trillion stars that we can potentially observe. Sounds like a lot, doesn't it? Here's the devastating truth. It might be nothing. If the universe is infinite, and the best evidence suggests it is, then the observable universe is an infinitesimally small fraction of what exists. Imagine picking one grain of sand from all the beaches on Earth. That grain is larger, proportionally, than our observable universe compared to an infinite cosmos. The question of infinity has haunted cosmologists since we first understood the universe expands. If space extends forever, then everything that can exist does exist somewhere. An infinite universe contains infinite galaxies, infinite stars, infinite planets. Somewhere out there, infinitely far away, is an exact duplicate of Earth, an exact duplicate of you, reading these exact words. In fact, there are infinite duplicates, scattered across infinite space. This isn't science fiction, it's a logical consequence of infinity combined with quantum mechanics. Matter can only arrange itself in a finite number of ways within a finite volume. If space is infinite, every possible arrangement must repeat eventually, including the arrangement that is you, your life, your memories, everything. But we'll never meet those duplicates, never communicate with them, never even know they exist, because infinity lies beyond our cosmic horizon. Light from those distant regions will never reach us. The space between us expands faster than light travels. We're confined to our observable bubble, roughly 93 billion light-years across, while infinity stretches beyond in every direction. The math here becomes disturbing. If the universe is infinite, then the observable universe, everything we can ever see, measure, or interact with, is exactly 0% of what exists. Not almost zero, not very small, literally zero. No matter how large a finite region is, its proportion of infinity is zero. Think about what this means for knowledge. We're trying to understand the universe using a sample size of 0%. Imagine trying to understand human civilization by studying one bacterium on one person's finger. That bacterium has more information about humanity than we have about an infinite universe. Maybe we're lucky. Maybe we inhabit a typical region, and the rules we discover apply everywhere. But maybe we're not. Maybe the physics in our region is unusual. Maybe other areas have different fundamental constants, different laws of nature, different types of matter. If the universe is infinite, anything that can happen does happen somewhere, including regions where physics works completely differently than here. This creates something philosophers call the cosmological horizon problem. We can only make statements about what we observe, but what we observe might not be representative. The universe beyond our horizon could be wildly different, and we'd have no way to know. Our theories might be correct locally, but wrong universally. Some physicists argue this makes the concept of the universe meaningless. If we can only observe one finite bubble, then that bubble is our entire universe. Everything beyond it might as well not exist. It can never affect us. We can never affect it. There's no causal connection whatsoever. From a practical standpoint, the universe is only the part we can interact with. But that feels unsatisfying, like denying that the moon exists when you're not looking at it. Those distant regions are real. They contain matter and energy, and probably life, and certainly structure. They're not separate universes in different dimensions. They're the same space, the same time, just unreachably far away. Calling them not our universe is semantic gymnastics to avoid uncomfortable infinities. The reality is we're trapped in a bubble of knowable space surrounded by infinite unknown space. We can study our bubble meticulously, measure its properties, map its structures, understand its evolution, but we'll always be uncertain whether our conclusions apply beyond what we can see. This is the ultimate limitation of cosmology. Not technology, not funding, not time, just the fundamental physics of causality and light speed. No matter how advanced our instruments become, no matter how clever our theories, we'll never observe more than a finite fraction of an infinite whole. We're like explorers on a sphere who've been told the world might extend infinitely in every direction. We can map our local region, chart its features, understand how it works, but we can't know if the territory 1,000 miles beyond looks the same or completely different. We can't know because we can never go there. The horizon keeps pace with us, no matter how far we travel. And as the universe continues expanding faster, that horizon isn't expanding with our exploration, it's shrinking back toward us, hiding more of reality with every passing moment. Right now, as you hear these words, galaxies are vanishing, not dying, not exploding, simply crossing an invisible line beyond which their light can never reach us again. Scientists have calculated the rate roughly 20,000 galaxies per second slip beyond our cosmic horizon. That's 1.7 billion per day, 630 billion per year. Picture watching a time-lapse of the night sky spanning billions of years. You'd see distant galaxies growing dimmer, redder, fainter. One by one, they'd fade to black. Not randomly scattered disappearances. Whole regions of sky would go dark as clusters cross the threshold together. The observable universe would shrink before your eyes. This isn't theoretical, it's happening right now at a measurable rate. Astronomers track recession velocities, how fast galaxies are moving away from us. When that velocity exceeds the speed of light due to cosmic expansion, the galaxy has crossed the point of no return. Any light it emits after that moment will never bridge the growing gap between us. Think about the math. 20,000 galaxies per second. Each galaxy contains an average of 100 billion stars. That means 2 quadrillion stars are crossing beyond our reach every single second. 2,000 trillion solar masses of matter, planets, nebulae, black holes, everything, all becoming forever unobservable. Here's what makes this process so final. When a galaxy crosses the horizon, there's no reversing it. Cosmic expansion is accelerating. Dark energy grows stronger. The galaxy doesn't slow down and drift back into view. It races away faster and faster, carried by space expanding at speeds no force in physics can overcome. Each vanishing galaxy takes its information with it. If intelligent life existed there, we'll never know. If they built civilizations, discovered physics we haven't learned, created art we can't imagine, all of it becomes permanently inaccessible, not locked away, not hidden, simply beyond the range where information can ever travel between us. The loss isn't symmetric either. When a galaxy crosses our horizon, we simultaneously cross theirs. Any civilizations there would watch our Milky Way fade and disappear. If they sent signals toward us, those signals would never arrive. If we sent signals toward them, same result. The separation is mutual and absolute. Future astronomers will inherit a poorer universe, not because matter is being destroyed, but because the observable portion is shrinking. In 100 billion years, as mentioned before, only galaxies in our local gravitationally bound group will remain visible. Everything else will have crossed the horizon. The sky will contain about 50 galaxies instead of 200 billion. But the process doesn't stop there. Even within our local group, some galaxies might eventually be pulled away by tidal forces or chance gravitational interactions. Over trillions of years, the number of visible galaxies could drop to 30, then 20, then 10. The observable universe will become a small cluster of neighbors surrounded by absolute darkness. This creates a tragic scenario for knowledge preservation. Everything we learn about distant galaxies, their formation, evolution, death, applies to objects we can study now. Future civilizations won't have access to those same objects. They'll have to trust historical records claiming billions of galaxies used to exist, but they'll have no way to verify those claims. No independent observations. No way to test theories against reality. Imagine being told that massive structures used to fill the sky, but you can only see empty space. Would you believe it? Or would you assume your ancestors were mistaken, that their telescopes were flawed, that they misinterpreted what they saw? Future astronomers will face this exact dilemma. The universe is erasing its own history, not by destroying evidence, but by making it unreachable. Every galaxy that crosses the horizon takes a piece of truth with it. Every star that vanishes removes data from the cosmic record. The universe is becoming unknowable, not because it's changing, but because we're being separated from it. And if dark energy continues strengthening, the separations won't stop with distant galaxies. Dark energy is currently ripping the universe apart at the largest scales, separating galaxy clusters, expanding voids, pushing matter into isolation. But what if it doesn't stop there? What if dark energy keeps getting stronger until it tears apart galaxies, then stars, then planets, then molecules, then atoms, then even the fundamental particles that make up matter itself? This scenario is called the Big Rip, and it's one of the most horrifying ways the universe could end. The theory is simple but devastating. If dark energy's strength increases over time rather than remaining constant, there will come a moment when its repulsive force overpowers every other force in nature, including the forces that hold matter together. Here's how it would unfold. Right now, dark energy only dominates at cosmic scales. Gravity still holds galaxy clusters together. Electromagnetic forces still bind atoms. Nuclear forces still keep protons and neutrons intact. Dark energy is too weak at small distances to matter. But if dark energy strengthens, if the repulsion grows exponentially, eventually it becomes strong enough to overcome gravity within galaxy clusters. At that point, clusters tear apart. Galaxies that have orbited each other for billions of years are ripped away from each other and scattered into the expanding void. The timeline is impossible to predict without knowing exactly how dark energy evolves. But physicists have run the numbers for various scenarios. In one model, galaxy clusters rip apart about 60 million years before the final end. Stars are torn from their galaxies about 3 months before the end. Earth is ripped from its orbit around our star about 30 minutes before the end. Then it gets worse. As dark energy continues strengthening, it overcomes the electromagnetic forces holding molecules together. Water breaks apart into hydrogen and oxygen. Rock crumbles into constituent atoms. Your body, everyone's body, every living thing disintegrates into a cloud of individual atoms. This happens about 30 seconds before the end. But dark energy doesn't stop. It keeps growing stronger, overcoming even the nuclear forces binding atomic nuclei. Atoms explode into protons, neutrons, and electrons. Matter as we know it ceases to exist. This happens a fraction of a second before the final moment. In the last instant, dark energy becomes so powerful that it tears apart even quarks and electrons, the fundamental building blocks of matter. Space itself might fracture. The fabric of reality could rip like overstretched cloth. The universe would end not in cold silence, but in catastrophic disintegration, where everything, matter, energy, space, time, shreds into meaninglessness. The good news: this is probably not our future. Most measurements suggest dark energy's strength is constant, not increasing. It's powerful enough to expand space, but not powerful enough to overcome gravity or electromagnetic forces at local scales. We appear to live in a universe heading toward heat death rather than the Big Rip, but probably is doing a lot of work in that sentence. We don't actually know what dark energy is. We can measure its current effect, but we can't predict its future behavior with certainty. If dark energy is the cosmological constant Einstein proposed, it stays forever constant. If it's quintessence, a dynamic field that changes over time, it could weaken, strengthen, or oscillate unpredictably. Some observations hint that dark energy might be getting stronger. The Hubble tension, the disagreement about how fast the universe is expanding, could be explained if dark energy was weaker in the past and stronger now. If that's true, extrapolating forward suggests continued strengthening, and continued strengthening leads, eventually, to the Big Rip. How long do we have? If the Big Rip is real, best estimates put it about 22 billion years in the future. That sounds like forever, but it's less than twice the current age of the universe. In cosmic terms, it's tomorrow. The Big Rip forces us to confront the fact that dark energy isn't just pushing galaxies apart. It's a fundamental force capable of overpowering everything else in physics. Right now, it's weak at small scales. But if it grows stronger, nothing is safe. Not galaxies, not stars, not atoms, not even the quantum fields underlying reality. We're living in an era when dark energy is still gentle, when its effects are barely noticeable in everyday life. But the universe is accelerating into an unknown future where that gentleness might not last. And even if we avoid the Big Rip, the spaces between galaxies are already emptying faster than we realized. Star formation is dying, not just in one galaxy or one region, across the entire universe. Astronomers have measured the rate at which new stars are born over cosmic history, and the peak is behind us. The universe formed more stars 10 billion years ago than it does today, and the rate is dropping. Here's why this matters. Galaxies don't appear fully formed. They grow over billions of years, accumulating gas and dust, igniting new stars from that material. In the early universe, galaxies formed rapidly because gas was abundant. Clouds of hydrogen and helium filled the space between young galaxies, ready to collapse into new structures. But as the universe expanded, that gas spread out, thinned, dark energy pushed galaxies farther apart, and the gas between them expanded with the space. Less gas means fewer opportunities for new galaxies to form. The raw material for cosmic structure is being diluted across ever larger volumes of space. Current measurements show the star formation rate has dropped by roughly 95% from its peak. The universe once created the equivalent of 10 new stars, like our own, every year. Now it creates less than one, and the decline is accelerating. This creates a disturbing timeline. Most galaxies in the universe have already formed. We're living in the era when the last generation of large galaxies is still condensing from gas clouds. Future gas will be too dispersed, too thin, too scattered by expansion to collapse into new structures. The census of galaxies we see today is essentially final. No new galaxies will form in our local region. The Milky Way, Andromeda, and the few dozen other galaxies in our group, this is our permanent neighborhood. There won't be fresh additions. No new structures emerging from surrounding voids. The sky will contain exactly these galaxies until they eventually merge or drift apart. But even existing galaxies are running out of fuel. Star formation requires hydrogen gas. Galaxies contain reserves of this gas, but it's not unlimited. Every time a star ignites, it locks away hydrogen into helium and heavier elements through fusion. Some gas is recycled when stars die, but much of it becomes permanently unusable, trapped in white dwarfs, neutron stars, or black holes. Scientists estimate most galaxies will exhaust their star-forming gas within 1 to 5 trillion years. After that, no new stars will form. Existing stars will burn through their fuel and die. Red dwarfs, the smallest, longest-lived stars, can burn for 10 trillion years. But eventually even they'll go dark. The universe will enter what cosmologists call the degenerate era. All normal stars will have died. The only light will come from cooling stellar remnants, white dwarfs fading from white to orange to red to brown to black. Even this dim light will eventually fail. In about 100 trillion years, the last white dwarf will cool below visible wavelengths. The universe will go truly dark. Now, combine this with cosmic expansion. Not only are galaxies running out of gas to form new stars, but they're also being separated faster and faster by dark energy. The space between galaxies grows. The voids expand. Matter concentrates into smaller, more isolated regions while emptiness multiplies. This means the universe is simultaneously dying and spreading apart. Stars are fading while the space they occupy grows. In the far future, the few remaining glowing embers will be separated by voids spanning hundreds of billions of light years. Each ember will be alone in an expanding darkness, too far from any neighbor to communicate or interact. The tragedy is that this wasn't inevitable. If dark energy didn't exist, the universe would eventually stop expanding or even contract. Galaxies would cluster closer together. New structures would continue forming as gravitational attraction pulled matter together. Star formation might slow but wouldn't cease entirely. Dark energy changed that future. By accelerating expansion, it ensures that matter spreads too thin for new structures to form. By pushing galaxies apart faster than gravity can pull them together, it guarantees increasing isolation. The universe isn't just expanding, it's being actively sterilized of new growth. We exist in the fertile era, when stars still form abundantly, when galaxies still cluster, when the universe is still young enough to create rather than just decay. But that era is ending. The raw materials are running out. The spaces are growing too large. The cosmic garden is wilting. And the few islands of matter that remain will eventually merge into even smaller, lonelier structures. Gravity is losing the cosmic war, but it's winning a few local battles. While dark energy tears the universe apart at large scales, our little corner of space tells a different story. The Milky Way and Andromeda are actually moving toward each other at about 70 miles per second. In roughly 4 billion years, they'll collide. Don't panic. Galactic collisions aren't like car crashes. Galaxies are mostly empty space. When two galaxies merge, their stars pass between each other with room to spare. The odds of any two stars actually colliding are astronomical, but their collective gravity will reshape both galaxies, stirring stars into new orbits, triggering bursts of star formation as gas clouds compress and ignite. The merger will take about 2 billion years from first contact to final combination. During that time, the night sky from Earth will be spectacular. If Earth still exists by then, Andromeda will grow larger in our sky, eventually spanning 6 times the width of the full moon. Its spiral arms will distort and wrap around our own. Stars will be flung into massive tidal streams arcing across the heavens. Eventually, the two galaxies will settle into a single elliptical galaxy. Scientists have already named it Milkomeda. This new supergalaxy will contain roughly 1 trillion stars and span about 200,000 light-years across. It will be the dominant structure in our local neighborhood. But the merger won't stop there. The local group contains about 50 other galaxies, most of them small dwarfs. Over the next 10 to 20 billion years, these will also merge into Milkomeda. The Triangulum galaxy will be absorbed. The large and small Magellanic Clouds, currently orbiting the Milky Way, will spiral inward and join the growing mass. Every gravitationally bound object in our region will eventually become part of one massive structure. This process is happening because gravity operates on a different scale than cosmic expansion. Within galaxy clusters, the gravitational attraction between galaxies is strong enough to overcome dark energy's push. Objects bound together by gravity will stay together regardless of how fast space expands around them. Think of it like a rope tying two boats together while the ocean current pulls them away from shore. The current pushes both boats, but the rope keeps them close to each other. The distance to shore increases, but the distance between boats remains fixed. That's what's happening in the local group. But here's the critical part. This only works for structures already bound together. Galaxies outside our local group are beyond gravity's reach. The space between us and them is expanding too fast for gravity to pull them back. They're not tied to our boats. They're drifting away with the current, accelerating into the distance. In 100 billion years, Milkomeda will be surrounded by darkness. Every galaxy outside our local group will have receded beyond the cosmic horizon. The Virgo cluster, containing thousands of galaxies, will be gone. The Coma cluster, gone. The Great Wall of Galaxies, stretching hundreds of millions of light years, gone, all of it pushed beyond the edge of the observable universe by relentless expansion. Future astronomers in Milkomeda will look up and see one galaxy, just one, a massive elliptical structure containing about 1 trillion stars. They'll catalogue those stars meticulously, study their orbits, measure their properties, and they'll see nothing else. No neighboring galaxies, no distant clusters, no cosmic web, just their galaxy surrounded by infinite emptiness. They might wonder if other galaxies exist somewhere in the darkness, but they'll have no evidence, no observations to confirm it. The cosmic microwave background will be too dim to detect. The expansion of space will be too subtle to measure with only one galaxy visible. Every piece of evidence that once proved the Big Bang happened, that other galaxies exist, that the universe is vast and populated, all of it will have vanished. They'll look at historical records claiming billions of galaxies once filled the sky. They'll read about quasars and galaxy clusters and cosmic structure, and many will think it's myth, ancient stories that our ancestors told themselves to feel less alone, because the sky they see shows only isolation. This is the ultimate irony of cosmic evolution. Gravity will pull our local matter together into a grand, unified structure. We'll have more stars in our galaxy than ever before, more planets, more potential for life and civilization, but we'll be completely alone, cut off from the rest of the universe by an insurmountable wall of expanding space. The universe is simultaneously concentrating matter and isolating it, building islands, while drowning them in an ever-growing ocean, and eventually, even those islands will go dark. Fast forward 100 trillion years into the future, Earth no longer exists, consumed by our dying star billions of years ago. The Milky Way and Andromeda have merged into Milkomeda. Most stars have exhausted their fuel and died. The galaxy is now a graveyard of stellar remnants, white dwarfs, neutron stars, black holes. But some stars still shine. Red dwarfs, the smallest, most efficient stars, can burn for 10 trillion years. A few of them are still flickering in the darkness, though their light is dim. Each one sits alone, separated from its neighbors by dozens of light years of empty space. The galaxy has become a sparse scattering of dying embers. Look up at the night sky from a planet orbiting one of these last stars. What do you see? Mostly blackness. The nearby stars are so faint and so far apart that they barely register. No bright constellations. No Milky Way band across the sky. Just a handful of dim red points scattered across absolute darkness. Every galaxy outside your own has vanished from view. Not just beyond the horizon. Even if they were still visible, they'd all be dark anyway. Every other galaxy in the universe faces the same fate. Stellar populations dying, light fading, structure collapsing into an expanding void. The universe is entering the black hole era. This is the period when black holes become the dominant structures. All the matter that didn't get locked into stellar remnants has collapsed into these gravitational singularities. Supermassive black holes at the centers of old galaxies contain billions of times the mass of our former star. Smaller black holes from dead massive stars dot the darkness. But even black holes aren't eternal. Stephen Hawking proved they emit radiation through quantum effects near their event horizons. This Hawking radiation is incredibly weak. For a black hole the mass of our former star, the temperature is 1/10,000,000th of a degree above absolute zero, but over incomprehensible stretches of time, black holes lose mass and eventually evaporate completely. Small black holes evaporate faster than large ones. A black hole with the mass of our former star would take 10 to the 67th power years to evaporate. That's a 1 followed by 67 zeros. Far longer than the current age of the universe. Supermassive black holes take even longer, 10 to the 100th power years. While this evaporation unfolds, the universe keeps expanding. The space between black holes grows. The remnants of galaxies drift farther apart. Dark energy continues pushing everything away from everything else. The voids expand until they dominate all of space. Eventually, after timescales so long that human minds can't comprehend them, even the black holes will be gone, evaporated into faint radiation that disperses through expanding space. At this point, the universe contains only isolated particles, electrons, positrons, photons, neutrinos, separated by unimaginable distances. These particles move through space that expands faster than they can ever meet each other. This is called the dark era. No stars, no black holes, no structures, just individual particles scattered across infinite expanding space. The universe has become as empty as it can possibly be. The temperature approaches absolute zero. Energy spreads so thin that nothing interesting can ever happen again. The night sky in this era, if anything existed to observe it, would be perfect blackness. Not the blackness of space between stars, where distant galaxies still shine. Not the blackness of a void surrounded by matter. Absolute blackness. No light sources anywhere. Nothing to see in any direction. The universe has become indistinguishable from non-existence. This is the heat death, the final equilibrium state where entropy has maximized and nothing changes anymore. Every particle sits in its own causally disconnected region of space. Every photon has been stretched to infinite wavelength. Every joule of useful energy has been dispersed beyond recovery. The process takes about 10 to the 120th power years. That's so far in the future that comparing it to the current age of the universe is like comparing the current age to a single second. We exist in the first moments after the Big Bang compared to this timescale. The era when the universe is still bright and full of structure is extraordinarily brief. Future will be dark, empty, dead, not because something catastrophic happened, but because this is the natural end state of a universe governed by expanding space and entropy. The light and life we see around us now is a temporary aberration, a brief flash of complexity before the long darkness claims everything. And the darkness is winning because emptiness is what the universe prefers. Entropy always increases. That's not philosophy, it's the second law of thermodynamics, one of the most fundamental rules in physics. Heat flows from hot to cold. Order becomes disorder. Concentrated energy disperses. Nothing can stop this process. Nothing can reverse it. And given enough time, it leads to absolute equilibrium where nothing changes anymore. The universe started in a state of incredibly low entropy. Right after the Big Bang, all matter and energy were packed into a tiny, hot, dense state. This concentration represented enormous potential for change, for structure, for complexity, and immediately entropy began increasing. Stars formed from clouds of hydrogen. They burned their fuel, converting ordered nuclear energy into disordered heat and light. That light spread through space, growing cooler and more dilute. The stars eventually died, leaving behind dark remnants. Each step increased total entropy. Life is the universe's most impressive attempt at fighting entropy locally. Living organisms maintain complex structures by consuming energy and dumping waste heat into their surroundings. We decrease our internal entropy at the expense of increasing environmental entropy even more. We're not breaking the second law, we're exploiting temporary gradients in energy concentration, but those gradients are disappearing. Stars are running out of fuel. The temperature differences between hot and cold regions are diminishing. The universe is becoming more uniform, more spread out, more equal in temperature everywhere, and as it does, the opportunities for life to exist are vanishing. Life requires disequilibrium. Hot stars surrounded by cold space, dense planets near empty voids, chemical gradients that can be exploited for energy. These differences won't last. In trillions of years, all stars will be dead. All temperature differences will have equalized. The universe will reach the same temperature everywhere, just a fraction above absolute zero. This state is called heat death, but that's misleading. The universe won't be hot, it'll be cold. Incredibly, impossibly cold. But more importantly, it'll be uniform. No temperature differences means no energy gradients. No energy gradients means no way to do work, no way to build structures, no way to support life. Think about what this means for consciousness. Right now, your brain operates by exploiting chemical gradients, sodium and potassium ions, flowing across cell membranes, creating electrical signals. This process requires energy. That energy comes from food, which ultimately comes from stars via photosynthesis or other mechanisms. Without stars, without energy gradients, consciousness becomes impossible. The universe will contain particles, photons, electrons, neutrinos, but they'll be so spread out, moving through space that expands so rapidly that they effectively never interact. Each particle exists in its own isolated bubble of space, separated from all others by distances that light can never cross. In this state, time becomes meaningless. When nothing changes, when no events occur, when no interactions happen, time still technically passes, but there's no way to measure it or experience it. The universe enters a timeless void where the distinction between one moment and the next disappears. Some physicists speculate about ways life might persist even in this era. Maybe advanced civilizations could harvest energy from black hole evaporation. Maybe they could slow their metabolisms to infinitesimal rates, thinking one thought every trillion years. Maybe quantum fluctuations in the vacuum could provide microscopic amounts of usable energy. But these are desperate speculations. The math is clear. Entropy always increases, energy always disperses, and the end state is always equilibrium. The universe is marching inexorably toward a condition where life, any kind of life, any form of complexity, any structure whatsoever, becomes physically impossible. The timeline is so vast it's almost comforting. Heat death lies 10 to the 1 to 100 power years in the future. Humanity will be long extinct by then. Our star will die in only 5 billion years. Even if we somehow survived, spread across the galaxy, engineered ourselves into forms we can't imagine, we'd still face the same end. But here's the existential weight of it. We exist in a universe that's dying. Not quickly, not dramatically, but inevitably. Every star that shines brings the universe closer to cold darkness. Every galaxy that forms uses up energy that can never be recovered. The process that created us is the same process that will end everything. And the reason for all this death? Emptiness is simply what space wants to be. Matter is the exception. Space is the rule. For every atom in the universe, there are billions of cubic light-years of empty void. We live on a dense rock orbiting a nuclear furnace, surrounded by other atoms, so we think matter is normal. But step back and look at the cosmos as a whole. We're islands of complexity in an ocean of nothingness. And the ocean is winning. Physics explains why. Creating matter requires energy. Shortly after the Big Bang, temperatures were so high that energy could spontaneously convert into particle-antiparticle pairs. Quarks and antiquarks popped into existence, collided, annihilated back into energy. The universe was a seething soup of particles, constantly appearing and disappearing. As the universe expanded and cooled, this process slowed. Eventually, temperatures dropped below the threshold where new particles could form. Most matter and antimatter annihilated each other, leaving only a tiny excess of matter, about 1 particle per billion that existed originally. That tiny excess became everything we see today. The rest became photons. Empty space contains about 400 photons of cosmic microwave background radiation per cubic centimeter. Sounds like a lot, but these photons carry almost no energy. Their temperature is just 2.7 degrees above absolute zero. They're the leftover heat from creation, cooled and diluted by expansion. Meanwhile, space itself keeps growing. Every second, billions of cubic kilometers of new void appear throughout the universe. Not appear, as in created from nothing. Space doesn't work that way. The existing space stretches, expanding the distances between objects. As it does, the density of everything drops. Matter spreads thinner, energy disperses, the universe becomes emptier. This is the natural trajectory. High energy states are unstable. They decay into lower energy states. Concentrated matter is temporary. It disperses under the influence of entropy and expansion. Empty space is the stable configuration, the state toward which everything trends. Even the quantum vacuum isn't truly empty. Particle-antiparticle pairs still pop into existence briefly before annihilating. These virtual particles exist for time spans so short that Heisenberg's uncertainty principle allows them to borrow energy from nothing. But they don't last. They can't accumulate. The vacuum remains essentially empty. Dark energy reinforces this trend. It's the universe's way of maintaining emptiness. Any region that becomes too dense experiences gravitational attraction that pulls matter together. But dark energy pushes back, expanding space, diluting the density. It's like a spring that resists compression. Try to concentrate matter too much, and cosmic expansion pushes it apart. The result is a universe where structure is temporary and emptiness is permanent. Galaxies exist for trillions of years, but that's nothing compared to the age the universe will eventually reach. Stars shine brightly but briefly before cooling into darkness. Even black holes evaporate eventually, leaving behind only empty space and faint radiation. Think about the ratio. The universe will spend its first few 100 trillion years in the stelliferous era, the age of stars. After that, it enters the black hole era, lasting until about 10 to the 100th power years. Then, the dark era, lasting essentially forever. If the universe's lifetime were compressed into a single year, the age of stars would last less than a millisecond, a brief flash at the beginning. Everything after would be darkness and expanding emptiness, stretching on indefinitely. We exist in that opening flash, the exceptional moment when concentrated matter and energy create complexity. This raises uncomfortable questions about meaning and purpose. If the universe's natural state is empty, dead, dark, what does it mean that we exist during the anomalous phase? Are we just a temporary accident? A brief fluctuation in an otherwise eternal void? Physics doesn't answer those questions. It just describes what is. And what is, unmistakably, is that emptiness wins. Structure is temporary. Complexity is fragile. The organized states that allow stars and galaxies and life to exist are fleeting aberrations in a universe that prefers nothingness. We're not living in the universe's prime. We're living in its infancy, the chaotic early era before it settles into its final state. Everything we see, everything we are, is built from borrowed time. The universe is slowly, inexorably, returning to the emptiness from which it emerged. And we're witnessing that process unfold right now, in this brief golden age when emptiness hasn't yet consumed everything. 13.8 billion years. That's how long the universe has existed. It sounds ancient. It sounds like forever. But compared to the timescales ahead, it's nothing. The universe is an infant, a newborn barely out of its first breath, and we exist in the nursery, the warm, bright, active phase before the long, cold adulthood begins. Right now, about half of all the stars that will ever exist have already formed. The other half are still being born or waiting to ignite from gas clouds. We're living through the peak of cosmic star formation. This is the era when galaxies shine brightest, when stellar light illuminates the most space, when the universe is most alive. In another 5 trillion years, most stars will have died. The last red dwarfs will still burn, but dimly. The universe will be darker, emptier, colder, but structures will still exist. Galaxies will still hold together. Black holes will still orbit each other. It won't be dead yet, just declining. In 100 trillion years, even the red dwarfs will go dark. The last normal stars will have exhausted their fuel. Only stellar remnants will remain, white dwarfs cooling toward absolute zero, neutron stars spinning alone in the darkness, black holes evaporating imperceptibly. The age of stars will be over, but the universe will still have trillions upon trillions of years ahead. The time between now and the end of stars is shorter than the time between the end of stars and the evaporation of the last black hole. We exist in the opening paragraph of a story that will take eternities to tell. Think about what this means. Every star you've ever seen, every galaxy in our telescopes, every structure we consider massive and eternal, it's all temporary. Humanity has existed for about 300,000 years. The dinosaurs lasted 165 million years. The oldest fossils on Earth date back 3.8 billion years. These time spans seem enormous to us, but they're microseconds in cosmic time, less than a blink. The universe will exist for tens of trillions of years after our star dies, for 10 to the 100th power years after the last black hole evaporates, for essentially forever after that, expanding and cooling and emptying indefinitely. The complexity we experience, the brief era when matter organizes into stars and planets and life, is a fleeting anomaly. This is both depressing and profound. Depressing because it means everything we are, everything we build, everything we accomplish is cosmically insignificant. The universe doesn't care about human civilization. It doesn't care about Earth or our star or even our galaxy. We're temporary patterns in matter that will disperse and fade like foam on an infinite ocean. But it's also profound because it makes this moment precious. We exist during the only era when the universe is knowable, when stars shine bright enough to see, when galaxies cluster close enough to observe, when the cosmic microwave background is still detectable. Future civilizations won't have access to this richness. They'll inherit a darker, emptier, lonelier cosmos. We're also lucky enough to exist when intelligent life can thrive. Stars provide energy. Planets provide stable environments. Heavy elements forged in supernovae provide the building blocks for complex chemistry. These conditions won't last forever. Eventually, the universe will become too diffuse, too cold, too empty to support life as we know it. Some scientists call this the Goldilocks epoch. Not too early, when the universe was too hot and chaotic, and not too late, when it will be too cold and empty. We're living in the middle ground when everything is just right for stars, planets, and consciousness to exist. Future observers looking back at our era will see it as the Golden Age, the time when the universe was young and vibrant, when galaxies filled the sky, when stars burned bright, when complexity flourished. They'll study the fossil record of cosmic history and wonder what it was like to live during humanity's time. And they might envy us, not because we achieved anything special. We probably won't survive long enough to matter on cosmic scales, but because we got to see the universe in its prime. We got to look up at a sky full of galaxies and wonder. We got to discover the Big Bang, measure cosmic expansion, map the large-scale structure. We got to be astronomers during the age when astronomy was still possible. The universe won't be this full, this bright, this knowable ever again. It's emptying, darkening, expanding into obscurity, and we're here to witness it, to document it, to understand it before the knowledge becomes unreachable. This is our cosmic responsibility, not just to ourselves or to humanity, but to the future. We must record everything we learn, preserve everything we discover, because civilizations that come after us won't be able to verify it. They'll have to trust our observations or remain ignorant of the universe's true nature. And what we've observed, what we've learned in these brief moments of clarity is terrifying. Here's the truth we've been circling around. The emptiness isn't coming someday. It's not a distant future problem. It's happening right now, every second, as you hear these words. The universe is disappearing before our eyes, and there's nothing we can do to stop it. 20,000 galaxies per second crossing beyond our cosmic horizon. 2 quadrillion stars per second becoming forever unobservable. Voids expanding faster than light can cross them. Dark energy tearing space apart at accelerating rates. The process isn't waiting, it's active, aggressive, relentless. Every photon arriving at our telescopes is older than recorded human history. We're not seeing the universe as it is, we're seeing its ghost, shadows of what existed billions of years ago. And those shadows are fading. The galaxies that emitted the light we observe tonight have already receded beyond reach. We're seeing their past, while their present vanishes into inaccessibility. This creates a haunting realization. The universe we study is already gone. When we point our telescopes at distant galaxies and marvel at their beauty, we're looking at structures that no longer exist in the form we observe them. They've evolved, changed, or receded so far that even light traveling at maximum speed can't keep up. We're cosmologists studying a dead patient, examining memories instead of reality. And it's getting worse. The rate of galaxy disappearance is accelerating. Dark energy grows stronger, or at minimum, maintains its strength while the universe expands, giving it more space to push against. Every year, we lose more galaxies from view than the year before. The observable universe is shrinking faster now than it did a billion years ago. Think about the implications. Future astronomers will have less data than we do. Less observable sky, fewer galaxies to study, less evidence of the Big Bang. Every generation of scientists will inherit a poorer, more limited view of reality. Knowledge won't accumulate, it will erode. This is why we see so much urgency in modern cosmology. Scientists rush to map the universe, measure everything observable, catalogue every galaxy within reach. Not because we're curious, though we are, but because we're running out of time. The universe is revealing its secrets during a narrow window, and that window is closing. If we don't document what we can see now, that information is lost forever. But documentation isn't the same as understanding. We still don't know what dark energy is. We can't explain why the universe is accelerating. We don't understand the full structure of reality beyond our cosmic horizon. We're watching something catastrophic unfold without comprehending the mechanism. Imagine being the last person to see an endangered species before it goes extinct. You take photographs, record observations, preserve samples, but you don't know why it's dying. You don't know how to stop it. You're just witnessing extinction in real time, helpless to intervene. That's humanity's relationship with cosmic expansion. The universe is teaching us a brutal lesson: impermanence. Nothing lasts. Not stars, not galaxies, not even the capacity to observe them. The cosmos we inhabit is temporary. The knowledge we gain is temporary. The very fabric of space that allows matter to exist is temporary, eventually tearing apart into isolation so complete that even particles become forever separated. And we're complicit, not through action but through existence. Every second we live, entropy increases. Every star that shines depletes its fuel. Every observation we make documents something that's already changing. We can't freeze time. We can't preserve the universe in its current state. We're passengers on a train heading toward darkness, watching the landscape fade from view through the windows. This is the terrifying answer to why space looks empty. It's not just empty, it's being actively emptied. Dark energy is draining the universe like water from a bathtub. The voids are expanding like infected wounds. The galaxies are fleeing like refugees from an unstoppable disaster, and we're witnesses to cosmic evacuation. The universe isn't winding down gently, it's fragmenting violently. Structures that should be eternal are being ripped apart on timescales shorter than we expected. The emptiness isn't patient, it's hungry. It consumes space faster than light can fill it. It swallows galaxies faster than we can catalogue them. It erases evidence faster than we can preserve it. We exist in the brief window between creation and oblivion, between the Big Bang's violent beginning and the heat death's silent ending. And that window is shrinking. The universe is less knowable today than it was yesterday, less observable, more isolated, more alone. This is why space looks empty, because emptiness is winning, because the universe's natural state is void, and we're watching it return to that state in real time, because every moment that passes takes us one step closer to a future where nothing exists but cold, dark, isolated particles drifting through infinite expanding space. The terrifying truth isn't that the universe will end someday, it's that the ending has already begun. The countdown started billions of years ago. The process is unstoppable, and we're living through it, watching everything we can see disappear into darkness that swallows stars, devours light, and erases reality itself from observable existence. The universe is telling us something through its emptiness. Everything ends, everything fades, everything disappears, and right now, this very second, we're watching it happen.